Hey everybody, Mr. Johnston here, and today we're going to do a quick review of photoelectron spectroscopy. In this video, I hope that you learn how to read a spectra to determine the identity of an element, the electron configuration, and be able to predict relative binding energies of electrons. I also would like to explain the exception to the trends in binding energies for electrons. First, I want to start with a quick review of electron configurations. So, in atoms, the electrons can be thought of as existing in shells or energy levels, and also in subshells or sublevels. Remember that the inner electrons are the core electrons, and the outer electrons are valence electrons. So if we look at this example electron configuration, as we look through here, the numbers in the front of each letter represents the shell or the energy level. The letters represent the subshell or the sublevel. And then the numbers that go along the top in the superscript indicate how many electrons are in that subshell. The Aufbau principle is an important rule to remember when talking about electron configurations. Aufbau is actually a German word which means to build up. And the Aufbau principle states that electrons fill lowest energy levels first and then fill to higher energy levels. So if we look at this energy level diagram here, we'll see that first electrons fill the 1s layer, and then they move into the 2s layer, then the 2p, 3s, and so on up the energy levels. Remember that each atomic orbital can hold 2 electrons. So each one of these atomic orbitals represents at most 2 electrons. So how do we know what the order is? And this is where photoelectron spectroscopy comes in, or PES, if I move my head out of the way. Photoelectron spectroscopy, PES. This is an experimental technique used to determine the relative energies of electrons in an atom. And photoelectron spectrometers use radiation, in other words, high-energy electromagnetic waves, or high-energy light, including ultraviolet light and X-rays, to remove electrons from an atom. These electrons, remember, are located in different energy shells or subshells. And the valence electrons, those are the ones that are easiest to remove because they are experiencing less attraction since they are farther from the nucleus. The core electrons are harder to remove. They experience more attraction because they are closer to the nucleus. Let's look at an example PES. So remember that the energies of electrons can be measured experimentally with PES. First, the position of the peak in a PES spectrum is related to the energy required to remove the electron. Also, you'll notice that on the y-axis, on the x-axis, the largest number, the highest binding energy, is furthest to the left or closest to the origin. The lowest number is furthest to the right. So we also usually think of like the origin or the corner of the graph as where the nucleus is located. And this is important because this kind of gives us the order that the electrons fill. Also, the height of each peak is proportional to the number of electrons in that subshell. So notice that the first layer here, there's just 2 electrons, so that's 1s2. And then the next subshell to fill would be 2s, and there's 2 electrons there. You'll notice that this third peak over is 3 times the height, and so there's 3 times the number of electrons. 2s2 compared to 2p6. 3 times the number of electrons, 3 times the height of the peak. And finally, we have 3s2. So when we actually go to try to identify what this element is, we can either count up the number of electrons, and that is the superscripts. So I would count 2 electrons, 4 electrons, 10 electrons, 12 electrons, and that would tell me the element is magnesium. Or I could just recognize that this is 3s2. 3s2 would be magnesium. So I know from looking at this electron, or this photoelectron spectroscopy, that this is the element magnesium. The other thing that we like to be able to do is make some comparisons for 2 different elements. So here I have photoelectron spectroscopy for beryllium and magnesium. And with this, I would like to point out that the valence electrons in beryllium have a higher binding energy. In other words, it takes more energy to remove those 2 electrons from beryllium compared to the valence electrons in magnesium. There's the bell. If you're at home, switch classes. Just kidding. Finish watching the video. So requires more energy because the electrons in beryllium, those valence electrons, I should say, in beryllium are closer to the nucleus. Therefore, they're going to have more attractive force compared to those in magnesium. Magnesium's valence electrons are farther away, and therefore the attractive force on magnesium's valence electrons is less than the attractive force experienced by beryllium's valence electrons. Another thing that's worth pointing out is the attractive force from the nucleus. And so here's 2 elements, carbon and oxygen. Carbon has 6 protons, whereas oxygen has 8 protons in its nucleus. And so if we looked at the core electrons for carbon, notice that the binding energy for carbon's core electrons is less than the binding energy for oxygen's core electrons. Because oxygen has more protons in its nucleus, it's going to have greater attractive force, and it's going to require more energy to remove those core electrons from oxygen compared to carbon. One other thing that I would like to talk about is kind of some exceptions. So here's 2 elements, phosphorus and sulfur. Now, just a reminder, phosphorus has 15 protons, whereas sulfur has 16 protons. And so it does make sense that if we compare like the core electrons, so first the 1s, sulfur, its core electrons require a little more energy to remove, and therefore have a little bit more ionization energy. And this trend continues through the core electrons, where each time sulfur is going to be just a little bit more energy to remove the electrons compared to phosphorus. And then when we get to the valence electrons, or the last shell, and by the way, the valence electrons for both sulfur and phosphorus consider everything in that 3rd energy level. Phosphorus has 5 valence electrons, sulfur has 6 valence electrons. But this last peak, for phosphorus, it's actually a little bit more energy to remove those electrons compared to sulfur. And so the question is, why? Why do the electrons in the 3p sublevel have a higher energy, higher ionization energy than the 3p electrons in sulfur? Well, in order to answer that question, we have to look at the orbital diagrams for each of these. And so if I look at the orbital diagrams for phosphorus and sulfur, phosphorus, it's 3p electrons. They are all unpaired. Whereas sulfur, its 3p electron, there is a set of paired electrons. And that means those paired electrons are sharing the same atomic orbital, which means that in this atomic orbital, those electrons repel each other just a little bit. And it turns out it's slightly easier to remove a set of electrons when they're paired up compared to when they are unpaired. And so we see that it's a slightly lower energy in sulfur on that 3p level compared to phosphorus in that 3p level. And that is the end of this video. Keep working on the lesson as you practice with some matching, and let me know or let Ms. Javner know if you have any questions.